Have you ever wondered why a hockey puck slides so far on ice, or why it's harder to push a full grocery cart than an empty one? The answers lie in the work of Sir Isaac Newton, who, over 300 years ago, defined the rules for how things move. His three laws of motion are the bedrock of physics. By understanding them, we can predict the outcomes of collisions, figure out how fast something will go, and even explain why we stay stuck to the Earth. Mastering these laws is the core goal of this unit. Before we get to the laws, we have to talk about force. Simply put, a force is just a push or a pull. You can't see a force, but you can see its effect. Forces are what cause objects to speed up, slow down, or change direction. In other words, they cause acceleration. Since forces have both a strength, magnitude, and a direction, they are called vectors. The official unit for measuring force is the Newton, named after Sir Isaac himself. Usually, objects aren't just being pushed or pulled by one force. Think about a game of tug-of-war. You have one force pulling left and another pulling right. The overall result is called the net force. To find the net force, you add up all the forces, making sure to account for their direction. If the net force is zero, the forces are balanced. If the net force is anything other than zero, that means the motion of the object is about to change. Newton's first law is often called the law of inertia. It states that an object will keep doing whatever it's currently doing, be it sitting still or moving at a constant speed in a straight line, unless a net external force acts on it. Imagine you're sliding a book across a frictionless table. That book would slide forever. On Earth, we don't usually see this because forces like friction and air resistance are always there to stop the motion. The concept of inertia is key here. Inertia isn't a force. It's a property of matter that describes how much an object resists a change in its state of motion. The more mass an object has, the more inertia it has. Think about pushing a baseball versus pushing a bowling ball. The bowling ball, with its much greater mass, has far more inertia, meaning it's much harder to get moving and much harder to stop once it is moving. The first law explains why seat belts are necessary. When you're riding in a car moving at 60 miles per hour, you are also moving at 60 miles per hour. If the driver slams on the brakes, an unbalanced force stops the car, but your body, due to its inertia, wants to keep moving forward at 60 miles per hour. The seatbelt provides the necessary opposing force to change your motion, preventing you from continuing forward toward the dashboard. If the net force is zero, we say the forces are balanced and the object is in equilibrium. This doesn't necessarily mean the object is sitting still. It just means its velocity is constant. A book sitting on a table is in equilibrium. The force of gravity down is balanced by the normal force up, but a satellite orbiting Earth at a steady speed is also in equilibrium. The forces on it are balanced, so its speed isn't changing. If the net force is not zero, the forces are unbalanced. This is where the action happens. An unbalanced force is the only thing that can cause an object to accelerate. Remember, acceleration isn't just speeding up. It's any change in velocity, including slowing down, deceleration, or changing direction, like turning a corner. If you see an object's velocity changing, you know an unbalanced force is at work. Newton's second law gives us a precise mathematical way to talk about unbalanced forces. The law states that the net force on an object is equal to its mass multiplied by its acceleration. This famous formula, F net equals m times a, shows that if you push something with more force, it will accelerate faster, assuming its mass stays the same. The acceleration is always in the same direction as the net force. The other crucial relationship in the second law is with mass. Imagine trying to push two shopping carts, one empty and one full of heavy groceries. If you push both with the exact same amount of force, the empty cart accelerates much faster than the full one. This shows the inverse relationship. For a given force, the bigger the mass, the smaller the resulting acceleration. That is exactly what the denominator in A equals F net by m tells us. The second law is the most useful for solving problems, and we often rearrange it to find acceleration. Vector A equals vector F over mass. It's important to keep track of units here. If the force is in newtons and the mass is in kilograms, kg, your acceleration will automatically come out in meters per second squared. Meters per second squared. Remember that a newton is defined by this equation. It's the force required to accelerate 1 kilogram of mass by 1 meter per second squared. It's easy to mix up mass and weight, but they are fundamentally different. Mass is the actual amount of matter in an object, which determines its inertia. Mass is measured in kilograms and never changes, no matter where you are. Weight, however, is a force, specifically the force of gravity acting on your mass. Since gravity changes depending on where you are, you weigh less on the moon than on Earth. Weight is variable, but your mass is not. To apply Newton's laws correctly, especially the second law, you need a way to track all the forces. That's where free body diagrams, FBDs, come in. We represent the object as a simple dot or a box, and then we draw arrows extending outward for every force acting on it. The length of the arrow represents the strength of the force. FBDs are the essential first step in solving almost any physics problem involving motion. One of the most common forces is gravitational force, F of g, or gravity. It's the attractive force between any two objects that have mass. On Earth, we experience it as the force pulling us down toward the planet's center. As we just discussed, this is the force that we call the object's weight. It's always the first force you draw on any free body diagram. When an object rests on a surface, like a book on a desk, the surface pushes back up to support it. This upward force is called the normal force, Fn. The term normal here means perpendicular to the surface. So the normal force always acts straight out from the surface, preventing the object from falling through it. On a level surface, the normal force is usually equal and opposite to the force of gravity, keeping the object in equilibrium vertically. Another pervasive force is friction. Friction is the resistance to motion that occurs when two surfaces rub against each other. It always acts in the direction opposite to the attempted motion. If you push a box to the right, friction acts to the left. We talk about static friction, which keeps an object at rest, and kinetic friction, which acts on an object that's already sliding. Friction is an unbalanced force that slows things down. Finally, we arrive at Newton's third law, the law of action-reaction. This is often misunderstood, but it's simple. Forces always come in pairs. Whenever one object exerts a force on a second object, the action, the second object simultaneously exerts an equal and opposite force on the first, the reaction. Crucially, these two forces are always equal in magnitude and opposite in direction. You cannot have a force without its partner. The key to the third law is remembering that the two forces act on different objects. Take a rocket launching into space. The action is the hot gas pushing forcefully down on the engine nozzle. The reaction is the gas pushing the rocket with an equal opposite force upward. That upward reaction force is the thrust that lifts the rocket. If the forces acted on the same object, nothing would ever move. You use the third law every time you take a step. When you walk, your foot pushes backward on the ground. That's the action. The ground, according to the third law, pushes an equal and opposite force forward on your foot, the reaction. It is this forward force from the ground that causes you to accelerate and move forward. You don't push yourself forward. The ground pushes you. In summary, Newton's 3 laws provide a complete framework for analyzing motion. The first law tells us when an object is happy not to accelerate, when the net force is 0. The second law gives us the math to calculate how much an object accelerates when the net force is not 0. And the third law explains the fundamental source of all forces, that they always come in equal and opposite pairs. Together, these 3 laws allow us to predict the motion of anything from a baseball to a billion-ton star.